Hello, and welcome to this video where we'll explore the simplest way to fine-tune the Llama 3.2 model, allowing you to create your own customized version. Llama 3.2 is a powerful open-source model developed by Meta, and our goal is to produce a fine-tuned version tailored to your needs. To accomplish this, we'll be using a popular library called Unsloth. Unsloth helps manage the process of taking the base Llama model and incorporating your own data to create a fine-tuned model. There are two main inputs for this process. First, we'll obtain our model weights from Hugging Face, and second, we'll provide our own text data. In this demonstration, we'll focus on a custom summarization use case. However, the principles we'll cover apply to various fine-tuning scenarios. You might be familiar with alternative libraries like Axolotl, but regardless of the tool you choose, you'll typically need Hugging Face and your own text data for the system to work. To keep things simple and accessible, we'll run everything on Google Colab. This approach allows you to follow along without significant expense. Let's begin by visiting the Unsloth Library homepage. While the web page itself doesn't offer much for our purposes, the GitHub source code is where we'll find a valuable example notebook. Although we're working with Llama 3.2, we'll use the Llama 3.1 notebook as a starting point and modify it as needed. On the GitHub page, you'll notice various model sizes listed. For our purposes, we'll focus on the Llama 3.2 models. We'll specifically look at the instruct format models rather than the multimodal vision options. When using Colab, the size of the model you can work with depends on the available accelerator. An A100 GPU is an excellent choice as it allows you to load the largest models. Keep in mind that using an A100 will consume more compute credits and increase costs. As we proceed, we'll need to choose both the model and maximum sequence length carefully. The system uses rope scaling, which supports any context length, but setting the length too high can lead to memory issues. We'll analyze our custom data to make informed decisions about these parameters. Let's create a folder called Data and add some example stories and summaries. The goal is to have long stories that our model will learn to summarize in a specific tone or style. We'll keep one story and summary pair, story 6 and summary 6, separate as a test set, excluding it from the training data. To properly analyze our data, we need a tokenizer. We'll use the AutoTokenizer class from the Hugging Face Transformers library to fetch the appropriate tokenizer for our chosen model. We'll select a quantized model from the Llama 3.2 options available on Hugging Face, such as the bits and bytes 4-bit model. This quantized approach helps reduce memory requirements and can improve performance. Now we'll import some additional code to analyze our data. This code will loop through our story and summary files, count the tokens in each, and print out the token counts. We'll provide this code in the video description so you can easily copy and paste it when following along. After running this analysis, we find that our longest example has been about 15,000 tokens. Based on this information, we'll set our maximum sequence length to 16,384, which is a round multiple of 1024, and comfortably accommodates our longest example. Next, we need to set two important parameters for the fine-tuning process, R and alpha. The R parameter measures how sophisticated our adapter layers are, while alpha is a weighting parameter that balances the use of the base model's intelligence versus our fine-tuning layers. A value of 32 for R is generally a good starting point, but feel free to experiment with these values. For data preparation, we'll remove the pre-existing code that suggests using an alpaca dataset from Hugging Face. Instead, we'll use our own data. We'll import the necessary libraries, including the Hugging Face datasets library. Now let's create a string template for our prompt. This template will include placeholders for our story and summary, as well as an end of string or EOS token. The EOS token is crucial as it tells the model when to stop generating text, ensuring our summaries don't continue indefinitely. We'll then create an array of fine-tuning examples by looping through our story and summary files. This process will combine each story and its corresponding summary using our prompt template. With our examples prepared, we'll create a dataset object. It's always a good practice to inspect your newly created dataset to ensure everything looks correct. We should see 5 rows, each with a text field containing our formatted story and summary. Now we're ready to train our model. We'll use Hugging Face's supervised fine-tuning trainer class for this purpose. Instead of setting a maximum number of steps, we'll specify the number of training epochs. An epoch represents one complete pass through all of our training data. For this demonstration, we'll start with just one epoch. As we initiate the training process, you'll notice that each batch contains 8 samples. Since we only have 5 example data points, our entire training process will complete in a single step. After training, we can test our newly fine-tuned model. We'll use our previously set-aside Story 6 as a test case. We'll feed this story into our model using the prompt template we created earlier and see what summary it generates. It's worth noting that we've set a relatively small number for the maximum new tokens parameter. If you find that the generated summaries are too short, you may want to increase this value to allow for longer outputs. Once we've generated our summary, we'll want to examine the output carefully. You might notice that the model includes an end-of-text token. When doing this right, during inference, this should not exist or should at least be at the end of the actual summary itself. Let's fix things up to make sure that's the case. An advanced technique you might want to explore is using the text streamer class from the Hugging Face Transformers library. This would allow you to get the output token by token, which can be useful for certain applications or for observing how the model generates text in real time. Now that we've successfully fine-tuned and tested our model, it's time to save it. It's important to note that we want to save the entire model, not just the adapter layers. This is because to use the model later, you'll need both the adapters and the base model. Saving to float16 format is a common and efficient approach. Next, we'll push our model to the Hugging Face hub. This step allows us to store our model and easily access it later. To do this, we'll need to log into Hugging Face and obtain an access token from our account settings. We'll use this token in our code to authorize the push to the hub. When pushing the model, we'll add a parameter to make it private, ensuring it's not publicly accessible. We'll also give our model a descriptive name. After successfully pushing the model, we'll receive a link to our new private model on Hugging Face. We can then download and use this fine-tuned model just as we did with the original base model. To summarize what we've accomplished, we've fine-tuned the Meta Llama model using the Unsloth library and Hugging Face tools. We used our own example data, processed it all in a Colab environment, and produced a Hugging Face ready fine-tuned model. This model can now be used in various environments for tasks similar to what we trained it on. In the video description, you'll find diagram files illustrating this process, along with the custom Python code we used in this notebook. We've also included the example dataset we used, so you can follow along even if you don't have your own data yet. If you have any questions or need further clarification, feel free to ask in the comment section. Also, if you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description. Thank you very much for watching to the end, and please enjoy responsibly.